So recall that last time I was talking about projective modules. So what is a projective module? That suppose P is projective if one will leave this covariant functor which is left exact becomes exact, which is same as P uh, is a direct summand of a free module. Again, which is same as any short exact sequence of this form always splits. So now today I will talk about what is an injective module. So Q is injective. Let us define injective module in this way that if I leave this contravariant functor from dash comma Q is exact. Remember it is also left exact, just like the other functor this. And so also I was talking about the Bayes criteria last time. And using that one can easily show that over a PID injective becomes divisible and vice versa. In fact, injective is divisible, that is always true as long as you are talking about an integral domain. You don't need to take a PID input. But anyway, let's say the proof. So both parts basically are the same way, just going around the same argument again. So suppose we have an injective module. And to show it is divisible, what you need to start with an element Q from that module and any non-zero element of that ring. And we need to produce some Q prime. We need some element of the module such that this chosen Q is R times Q. And so let us take this ideal and the module homomorphism by sending R to Q. So because it is injective, you get an extension from R to Q. And let us define Q prime as f tilde of 1. And then you can easily see that f tilde uh, of 1 is Q prime means R times Q prime becomes f tilde of R. But f tilde agrees with f on I, which is f of R, which is Q. And so as you can already see that we have not used the fact that it is PID. So this fact is independent as long as you are over an integral domain. But for the other fact, we'll use the fact it's a PID by taking, say, so we need to show that it is an injective. Means given any module homomorphism from any ideal I to Q, we need an extension. We need f tilde from R to Q, right? Such that f tilde restricted to I becomes f. And because R is a PID, this is generated by some elements smaller. And let us define Q to be f of R. And now, so we have an element R and an element Q. So we can apply the fact that Q is divisible. So we get some element Q prime, right? We'll get some element Q prime such that R times Q prime is Q. And remember, R as R module is generated by 1. So it is sufficient to know where 1 goes. So we can define 1 to go to this Q prime. And that is our f tilde. And again, you can see that f tilde on this small r is just r times f tilde of 1, which is r times q prime, which is just f of r, which is q, which is f of r. So it means f tilde restricted on I is f. Because I is generated by the element smaller, it is enough to see that they are agreeing on the generator. So yeah, so that is a nice characterization over a PID for injective modules. And from there you can see that the likes of Q mod Z or Q are injective Z module or injective abelian groups. Right? Okay. And so yeah, so we have talked about projective modules, injective modules, and this is a nice observation. Suppose you have a ring. So if R is a ring such that all R modules are projective. Now my claim is this is same as saying that all R modules are injective. Well, so this is really easy because so we'll use this criteria. And for injective module, I think I forgot to define or I forgot to mention that. So if Q is injective, that is you can show that if and only if any short exact sequence, this time starting from Q, always splits. So now come you can take these two statements to conclude that because suppose you have all modules to be projective over R, then if you start with any module Q and you get a sequence like this, you can see that because say so suppose you have R module Q and let's start with any short exact sequence of this one. Now because B is a projective module because we have assumed all R modules to be projective, you get a section in this way. And so let's call this, say this is F, this is G, let's call this G prime. So by the help of G prime, F and G, you can define another map F prime, which becomes a section in this direction. So you'll get that Q is injective. And similarly, if you assume all modules to be injective, we'll get that Q is any P is projective. That is again the same argument. But now you can take this as an exercise to find such a ring. Like, what is an example of such a ring such that all modules over the ring is projective or equivalently injective? So you can maybe try to find the example. It's not difficult. Yeah, I will come to it later with examples. Okay, so now we've talked about projective and injective module business. So let us now come to the next functor, which is related to the home functor, the tensor functor. So what it takes any module R module A and gives another R module and tensor. So just assume R is commutative just to make sense of the right module structure on M and A and so right or left module structure depending on. And similarly, you can take this functor as well, just like home functor, you can take functor on both variables. But the thing is, because these two modules are naturally isomorphic, there is no need to take two different things. So I will only go with this convention. Okay, so the first thing which is really important or really connecting this home and tensor businesses, it is the adjunction. What it says that there's a natural bijection between the following home sets. So this and between this. And let me just define the maps in both directions. You can verify their compositions or identity on respective domains. So psi of any F is a map between A to home, B and C. So what you do is you take any A, so psi F of A is a map from B to C, and it takes an element B and gives it to F of A tensor B. Remember, F was a chosen map from A tensor B to C. So this makes sense, right? And in the other direction, you can define phi and take an element F. So this will be a map between A tensor B to C. Okay, so as you know, to define a map from a tensor product, it is sufficient to find a bilinear map from the cross product or a direct product. Sorry. So we define a map between A direct product B to C, where A comma B goes to. So here your F is a map from A to harm B of C, right? So here f of A is a map from B to C. So you can apply B on. So you get an element of C, right? And you can verify this is a bilinear map because F was a linear map. So you get a bilinear map from this, and so from there you get a homomorphism in this direction, and you can verify that this psi and phi are inverses of each other. So this is the tensor adjunction. And so you know the home functor in both variables are left expected. And using these two following, let's say you can take this as an exercise as well. That suppose this is exact. So if say you can take any component, maybe I can take the contravariant version. Say Q to home, say BQ to home, CQ is exact. So this is for all Q. The arrow should be in this direction. Right? So, and now by the help of these two things, the adjunction in this small exercise, you can show that tensor is right equal. So tensor is right exact, meaning you, that given a short exact sequence, you apply the functor this. So it may not be exact here, but this part is always exact. So I will come to it in the next video. And I will also show some characterization of a flat module and also show that the relation that any free module is of course projective. That is by the characterization that every projective module sits inside of the direct summand of a free module. So any free module in particular is projective. And I will also show that any projective module is flat, but not the converse. I will provide some examples as well. So yeah, so that is what I will show in the next video, and I will also show the right ignorance of tensor functor using the adjunction. It is really easy. If you apply this result, you can see this. You can try this. So